All right, can you guys see my screen?
Yes.
Yes.
Yeah, okay, awesome. All right, so last week we spent some time, we talked about one-time pad, and then we tried, numerous different types of attacks, such as, choosing plain text attack and choosing ciphertext attack. And then we showed that it pretty much resists all these attacks, and it looked like to be a very good, you know, s- s- symmetric key encryption system. However, we mentioned that we can't just use it in practice because of the issue that the key has to be at the same length as your message. But the good thing about one-time pad is that it achieved like the highest amount of security. So that is still something that is attractive. And then later on, we will come back and see how we can utilize the idea of one-time pad. We just have to wait for the time to come. Today, we want to talk about a slightly different problem. And when the time comes, we would go and talk a lot about different public key cryptography algorithm, such as RSA. But so before we get to here, we talk about one-time pad and how it is perfectly secure, meaning that no matter how much computation time we give to the adversary can't break the system. But the other version of algorithms, on the other hand, are computationally secure, which means that as long as we assume that the attacker has limited computational power, then this sort of crypto systems can remain secure. Probably you heard a lot about them, so today we are here to talk a little bit more about these sort of computationally secure crypto systems or digital signatures. There are many of them actually that we use them in daily basis. But let's expand this a little bit more to understand what does this actually mean, and is it really insecure or it is reliable? So this is the goal. So the first thing is that we assume that the adversary or attacker computing power is polynomially bounded. So polynomially bounded might sound a bit awkward for many of you. So let me remind you the time that you do, like, let's say I give you two matrices and I ask you to multiply one matrix to the other matrix, and then you get some results, right? And then if you remember algorithm course, the first thing that really mattered in the algorithm course was the complexity of this problem. And then we said that some problems, such as matrix multiplication, not the most optimized one, that's just the original algorithm, the very basic algorithm, is actually we would denote it with like n cube. So we are saying that the order, the complexity of this algorithm to do this multiplication is n squared, where n is the number of the elements in this matrix. So, and then we have a bunch of different algorithms. Some of them are linear, some of them are sublinear, which we can run them much faster. Some algorithms are polynomial, and you can have this form n square plus n, square plus whatever. But the point is, they would have this format. And then we have also some algorithms that are exponential. So, and then you really felt with some small programs that you wrote that, when you convert or solve a problem in a different or a special way and turn these polynomials to the linear, and then you could see that for larger input, you can get the answer much faster. So what is that relationship has to do with here? So we are saying that our adversary has enough computational power so that he is able to run polynomial time, algorithms with no problem. which means that he would have, you can imagine he has a server or he has access to the PC, and then he has no problem running problems that are, have the complexity of polynomial time. And that is unfortunately the all amount of computation power that he has. And this is true for most of us. We have access to, as much as resources and servers, and you can buy. At the end of the day, you can solve all the polynomial time problems in a reasonable time. Maybe you can manage to do the computation a bit faster, but we can't really solve much of exponential problems because they would take some time, and some of them would take so long time that we don't even want to spend time to do it. Okay, so now we understand what is the notation of polynomial time bounded. So that is given. We want to exercise this polynomially bounded, and then we see that what does that has to do with some longer-standing problems such as RSA. So we know that we have this algorithm called RSA. So we would go through this algorithm very quickly, but I don't expect you guys to learn it, how exactly this algorithm works. We just want to see the steps in the computational manner. And then don't worry about it. In public key cryptography chapter, we would spend quite some time to deeply understand how RSA works, and we would prove it. But for the time being, let's say, how do we compute, we set up this RSA problem, and then so that we just want to see the steps, and we just want to see what a polynomial time adversary can do with it. So the algorithm starts with the key generation. In the key generation, the way that we would do is we would typically find two prime values. We would call them normally P and Q. These are some primes. And once we find these primes, then we will compute N, which is nothing but P times Q. Just multiply them together. And then, since we know P and Q, so we can compute some function called phi of N, which is a torsion function. And then its function is defined to be P minus 1 times Q minus 1. Okay. This function has a special meaning, but for now, for the time being, we are just interested into the computation. So actually allow me to write this down below so that we know the steps. So we find this prime in P and Q, we multiply them together. Then we would compute phi of N, which is just P minus 1 times Q minus 1. And then once we did that, we would choose some value E, which is less than N. We basically choose it to be random, let's say for this practice. So we would choose an element, a number, an integer that is just less than N. And this is going to be your public key in RSA. And then we would compute D to be as follows. We would compute D to be, or secret key is that we want to satisfy this equation so that E times D equivalent to 1 mod phi N. Okay, so this is how we would generate the public key and a private key. So now that this is computed, the public key of this user is going to be E and N, and then the private key is going to be D and N. Okay. What does this equation mean, and all those bunch of other questions that you guys have? It doesn't really matter here. As I said, we will come back to it and we would see why D has to be computed this way. But you can just, for now, you can take it that D is the multiply how the computation would, the equation is planned here. But I just want you to focus on the computation. So these are the steps that we took to be able to generate this public key and a private key. And then as you can see, we just found two prime numbers, we multiply them together, we compute the phi N, we just choose a random element, and then we just solve this equation. And then by the end of that, we would be able to output the public key and a private key. So if I just give you, tell you that all this computing this function is very, we can compute it very fast. So given that, because you're probably not familiar with this modular operations, but given that, we can see that we can actually compute all these steps in some polynomial time. So poly time. Because you know that multiplication is fast. This is again multiplication, and this is just like solving some sort of linear equation. So we can do all this computation in polynomial time, and we can do all of them quite fast. So now that we have the public key and we have the secret key or the private key, so then we can go ahead, and this is the encryption algorithm. For encrypting a message, we take the public key, and then we take m, we raise m to the power e, and we compute mod n. Mod n here means the remaining of this equation. So whatever m to the power e divided by n, and then this mod n here returns the remainder of this division. And then the decryption would work in the opposite way, and then we get the ciphertext and d and n, and then we basically raise ciphertext to the power d, mod n, and then we would get our original m back. So this is how encryption and decryption would work. So we just do basically exponential modular exponentiations. That's what we call it. All right. So this algorithm is shown to be computationally secure under ciphertext attack only. So we know the definition of the ciphertext when we only have a pair of encrypted version. So let's really plan this out and see how does this work. So, and then also it says that it is not perfectly secure. So let's really invest in that and see why is it so. So now we want to see this problem from Eve's perspective. Eve sees that, okay, we say that this problem is, we say that is computationally secure. So what Eve has access to is, of course, Eve knows the public key of this user, which is E and N. We said that public key is just email address. You can share it with everyone. And then also Eve knows, let's say a pair of message and its corresponding ciphertext. And then the goal of Eve is to basically try to see if she can compute D over here. So the first method that she can try is, let's call this one to be method number 1. She knows that she can try many different, private keys, because she knows that this D that we've generated over here is some integer less than n, right? So let me call this one DI. So then nothing can stop her to try different private keys. She would start to guess. Let's say she would choose D1 and N. She would let that one to be the secret key. And then she will try D2 and N. She can, basically choose many different private keys. And for any of them that she choose, she would check if she can match this equation. She can get the C, raise it to the power DI, mod N, and then she makes sure that if this one is equal to M or not. Okay, as long as she is able to find a DI, one of these D's, that once she raise C to the power DI and compute this modular operation over here, this returns M, then she knows that she has found the corresponding private key for this public key that is already published, E and N. So this is the first method that she can work through, and she can try to see if she can break this this idea. But do you guys have any opinion? Do you think this method is effective?
It depends on the what was it, the D or the N? The N, I think, because it needs to be smaller, the D. So if it's very big key space, then it's gonna take a lot of trial and error.
Right, yeah. So let me expand on that. So it looked like that the opinion is in the right direction. Let me see, what page was this one? 21. Actually, let's spend some time here and see what are the best options and what we can achieve at the end of the day. So this is a really important concept. I really want you guys to understand how difficult it is to break some of these, systems. So we talked about method number. I want to continue with this method. So method number 1, we said that Eve would try many different Ds, right? So she can guess, like maybe D1 is the private key, maybe D2 is, maybe D3 is, all the way to, some n different Ds. And for every D that she chose, we said that we have to compute to check if M equals to C to the power Di mod N. So let me tell you something, some piece of information. This operation, modular exponentiation, you can compute this piece of line in a logarithm order. So computing this is a logarithm order in the number of the bits of n. If you look at the n in a binary format, n maybe has 1,000 bits, so it would take only logarithm of 1,000 so that we can do this computation. So it is very fast. Okay. So now that I give you this idea, so if we want to write a pseudocode to solve this one, let's see how it works. So if I want to do this, I would say that for some D equals to 2, actually I want to try all possible one, right? 2 n, right? What I want to do is that I want to check if m equals to C to the power D mod n, right? If this is the case, and then just return D, right? And that is as simple as it looks like, right? So it's very easy code. And then, well, let's see how long will it take for us to do this for loop. So normally in RSA, actually today we would choose the RSA to be quite long, right? So we would choose some RSA that is at least 4,000 bits. But let's just imagine that it is 1,024 bits. So if I look at n in a binary format, I can represent n with 1,024 bits. So this is the number that we have. So now looking into this algorithm, given that n is such a long number, so the value of n with that many bits can be at max 2 to the power 1,024 minus 1, right? So yeah, imagine you guys want to write a for loop that continue to check these numbers up to 2 to the power 1,024 minus 1. This n would look like to be if you look at this n in a decimal format, we are talking about a number with 300 digits. So, if you have never tried, you can just fire up your laptop and try to write a for loop with some, dummy computation underneath with like, 10 to the 2, 10 to the 3, 10 to the 4, and so on and so forth. And then as you see that as you continue, so you would see that, the response would get smaller, slower and slower until sometime that when you run such a big thing, this would take quite some time. So imagine writing a for loop that you start from 2 all the way to a number that is 300 digits. I feel like if you want to write down that number, you would take a A4 paper, both sides, to just write down n. This is how big the n is. And these days we are talking about at least 4,000 bits, so it is way longer. So good luck with running this for loop and hoping that you get that D. So this for loop would take quite a long time to compute, but we would get back to it. So I would have some computation over here for you to kind of figure it out. How long will it take to do this sort of computation? So this is the one way to for Eve to break this system, given the information. And then the method number 2 says that, well, we can actually factor n. If we can factor n, if I know how to factor n, then I can find p and q. Then the rest of the computation Eve can do in a polynomial time, so no problem, right? So the only challenge is that if you know p and q, the rest of these lines could be computed very easily. So as we said, we want to factor n to a p and q, right? Let's be precise, such that n equals to p times q, right? And then if we know this thing, if we know this piece of information, then of course we can go ahead and do this computation in a polynomial time. So if we know that, then we can go ahead and do this computation and do compute D in polyline. Because we know the rest of the steps. And the problem was to find P and Q. So a small example, factorization, if I give you 15, n equals to, for example, 15, then I ask you what is the factorization of n, you need to give me 2 prime numbers so that when you multiply them, you get 15, right? So the numbers are 3 times 5. So this one is P, for example, and this one is Q. It doesn't really matter which one is P and Q. One is 1, the other one is the remaining one. So, okay, it looks like that if we somehow be able to factor n, then we would be able to do this to break the crypto system. But again, we assume that our n is large. So when n is small, well, we can do this computation very fast. But when n again gets large, we are talking only about large n, so 1024 bits. Then here comes the challenge. So actually, like if you just want to try, with a very simple pseudocode, and you want to see how it works, is that if you know, some prime p, and that prime p divides n, then you are supposed to get an integer. For example, this is our idea. So if we know p, right? Suppose I give you p, then you can easily compute q, because n divided by p, it would be q, right? Which is an integer, right? Interesting. So I don't have to find p and q. It just means that I just have to find one of them. Okay. So, okay. How do we find p? Anyone has any idea? If you want to find this p, that factors n, what is your suggestion? How do you think you can find it? Any opinion? All right, let's get to this. We said that p is prime. So one of the ways that I can do it is that I can say I'll divide it with all a small p that I know. So I start with 2, 3, 5, 7, 11, 13, and all the way to some let's say prime number to the square root of n, and all the way to all the prime numbers all the way to n. So these are, let's say, the set of prime numbers that are less than n, and our algorithm so far is to assume p is one of them, and then we divide n to one of these 2, 3, 5, 7, and so on and so forth. We will continue until the result of this division is become an integer. It's not fractional number, it is an integer, and that is going to be the right p because we can find q too. Okay, but there's a trick over here, and the trick tells us that we don't have to actually go all the way to the n, and only up to the square root of n would be enough. How so? Because we know that if we have a number that is 1024 bits, it means that roughly two numbers of 512 bits, we got them multiplied to each other, so that now we have a 1024 bit integer, right? So if you do a square root of n, which is 2 to the power 1024, we would get to some number which is 2 to the 512, right? So we only have to go all the way up to some integer, some prime number that is less than this value, and therefore we don't have to go all through all the list over here. So all the way up to a square root of n is enough. Okay. All right, so that is given. So at least that would drop a significant portion of this list that we have to try. But let's see how big is the portion that we have just now. Let's write the pseudocode for this one, so we better understand what are we talking about. So let me get this one. I did compute this one, and it is roughly equal to 10 to the power 150. I think we understand this number better than 2 to the power 512, right? So this value is roughly 10 to the power 150. So given that, I can write the pseudocode for this problem. I can say that for p equals to 2 to 10 to the power 150, check if p divided, check if n divided by p is integer, and if it is so, just return p. Right? So the steps are, let's go through it again. So we go all the way on until the half of this list, as we said, because when n is 1024 bits, this means that we had roughly two numbers that were 512 bits. We multiply them together, we double the bits, right? So that's by the rule of multiplication. So that suggests that we know that in RSA they choose a p and q that are roughly in the same size because of the security reasons, and also that helps us here. So then we need to check the prime numbers all the way up to this number, and this number, if we change the bases to 10, then it will become 10 to the power 150. And looking at this for loop, it looked like that. Okay, I'm not sure how many of you have tried to go anything close to this number. This number would take a really long time to do the computation. In order to really understand that, and I just want to give you an example. This is a very good example to really understand why do we mean by computationally difficult or hard. So let's do some math together. Suppose that you have a CPU of 3 gigahertz. So let's say I give you a CPU. You have 3 times 10 to the power 9, right, hertz, which is 3 gigahertz. And then, the example is like what we try to do is like, okay, suppose I give you a core like this, and I suppose that you had this CPU from the beginning of the universe. And then we want to see that how many computation of this for loop we could have run if we have started to do this computation from the beginning of our universe. So this is a very big claim. So let's see how what that means. So let's see some numbers. So the lifetime of universe is 10 billion years, right? Which is 10 to the power 10 years. Okay. And then in every year, let's see how much computation we could do. In every year, we have 365 days times 24 hours times 60 minutes times 60 seconds. We would be able to have roughly 2.4 times 10 to the power 6 seconds, right? Okay. So this is the amount of the seconds that we have in a year. Suppose we are starting to do this computation from the beginning of the universe. So, computing from what we would have. We have to multiply all these things to each other. So we would have, in every second we can do this many, and let's say in every clock of your CPU, you are able to do one of this for loop. Okay, we're gonna be very generous. So roughly we would have how many computation we could do? 3 times 10 to the power 9 multiplied to 10 billion years times 24, 2.4 times 10 to the power 6, right? This number over here. How many seconds do we have? And we would land to some number called 7.2 times 10 to the power 25. Okay. So if we suppose that if you had a CPU and you start to run this for loop from the beginning of the universe, and I also was very generous and I said that in every clock of the CPU, you can basically do all this computation. You can do one round of this for loop. Have we started from this beginning of the universe for 10 billion years with that CPU, we would be able to only cover 10 to the power 25. How much we should cover? 10 to the power 150. This is far less than what we could have afford to compute if we had started this algorithm from the beginning of the universe. Okay. Somebody would jump in and say that, what if I had access to parallel computing? You're just giving me one CPU, and I am only able to do this, on one CPU. What if, in the beginning of the universe, we had more cores and more CPUs? Then my answer is, of course. I suppose that we have 10 to the power 80 CPUs, computers. And this is roughly the number of the atoms in the universe. Remember, number of the atoms in the universe. I suppose that you have 10 to the power 80 processors, as many as the atoms that we have in our entire universe. And if we don't want to do the, if we want to be very generous, we can say that we multiply this number to what we have up here. And then again, you will see yourself that they are not even close to this number. So now I hope that it really start to understand that when we say some problem is computationally hard, I think this is a small example that I provided you here should really help you to understand that, have you had a very good CPU, a 3 gigahertz CPU, from that you started this computation from 10 billion years ago, and also you had 10 to the power 80 computers or cores, and by today you wouldn't be able to even get close to this number, 10 to the power 150. And again, as I said, for today computation, we would suggest to use RSA of 4,000 bits. So a square root of 4,000 bits, it would be 2 to the power 2,048 bits, which is far larger than what we have here, right? So you may say that, okay, in future, I will have more cores and more process and more stuff. And then my answer to you would be, as soon as I increase this value, again, you won't be able to do that computation fast. Because, you know, as I said, the computation that we need in RSA is all the modular exponentiation, is logarithmic, it's sublinear. So you get more compute, it means that I also get more compute. So, you know, if I increase the number of the bits, my algorithm complexity, you know, for computing RSA encryption, decryption is sublinear. So I don't really notice the difference. But for you, for you, I mean the attacker, if you want to do, you know, this many of computation for larger bits of RSA, good luck with that, because that is going to be extremely difficult. And of course, I'm only talking about classic computers. I'm not talking about quantum computers, because that is a very different story. But anyhow, I really hope that you have a good understanding of when we say some problem is computationally hard, we really mean that it is computationally hard. And you see that with these generous numbers and with this pseudo code that look like to be tiny and nothing, 10 to the power 150. But I think this example should really help you to understand that this is something that would really take a long time to compute, and it is not easy to do to go around this problem. So any questions around here? Anything you have in your mind? Okay, that sounds good. So now I want to go back to this slide and see and compare this with the previous results. So we had unconditional proof, you know, one-time path that we showed that it is basically perfectly secure, that unconditionally secure, that no matter how much computational power you provide to the adversary, at the end, all computational power, it would not be able to help the adversary in any way. And soon we would show with some formulas how so. But now we are talking about different class of crypto systems that we assume that the adversary is polynomially bounded. And this definition now, that is adversary is polynomially bounded, it would make sense to you more, because, you know, we were generous and we provided a lot of computational resources to our adversary. And then we see that even with a lot of computational power to our adversary, the adversary would not be able to, you know, break the system in a short time, right? But this does not mean that, you know, whenever you see computationally secure crypto systems, it does not mean that they can never break it. Eventually, the adversary would be able to break it, but, you know, we see that it would take a very, 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 very long time to break it. And by the time that they break the system, maybe the information doesn't have a value. Maybe like, I don't know, 20 billion years from now, somebody would be able to break a crypto system like RSA with a 1024-bit key. And okay, they store whatever they have transferred and encrypted with that crypto system. And now they are able to see what Alice sent to Bob in, you know, 20 billion years ago. And at that point, Alice and Bob won't care. So when it comes to some scenarios that, you know, the information has a timestamp, and after some timestamp, of course, it is not valuable anymore. This notation of computationally secure becomes very attractive because you know, the crypto systems that we can design here, they got very attractive properties that we can do a lot more than just simple encryption and decryption. And you know, thinking about it now, they have enough security for the lifetime of, you know, that message, or you know, or maybe our lifetime. And after that, we won't really care if somebody would be able to break the system and gain some information. So the reason that we say that eventually the adversary can break it, because looking into the equations in RSA, we can say that when we fix the public key and you know, you have the ciphertext C, there is only one M that would satisfy that equation, that over here. And it is computable in finite time. It is finite time because eventually your, you know, if you go back to the notation of computational complexity, eventually if you write it in a Turing machine, the algorithm would halt and output the results, the D, the secret key. But we know that it is acceptable and solvable in a finite time, but when we come to implement it with the current algorithms, we would see that even though it is a finite time algorithm, but it is obviously not a polynomial time algorithm, and the computation cost is a lot, and it would take a very, very, very long time until, you know, our algorithm halts and the for loop would return that P for us. So that is the observation that we had. And again, if you go back to the method number 1, and you see that for even method number 1, finding different, you know, D's, we would get back to the same issue. So these are 2 ways of breaking you know, RSA crypto system. I'm not saying these are the only ways. We would be able to see different ways, hopefully, along this this course. But I just wanted to plan out and stay a bit longer on this slide for you to really understand that when somebody says it's computationally secure, it doesn't mean that it's not secure. It doesn't mean that it is unrealistic notation. It is really practical, because we just saw that you know, with a huge amount of computation, our adversary was not able to break it on a reasonable time. So that's why we use this notation of polynomially bounded you know, adversary. And we would see that a lot of crypto systems that we would use these days are actually using they are actually computationally secure. All right, I think this is about the time for your break time. So let's have a break time for 10 minutes, and then we would come back and continue at 9 o'clock.